going to explain about priority queue based on leftist tree. So before going to introduction to leftist tree, I want to discuss about why we need the leftist tree. Suppose that we have two binary tree, one of m nodes and the another one of n nodes. We want to merge both of them. So we have to first arrange them in an array with of size m plus n, and after that we merge, and the time complexity of the merging both the binary tree becomes m plus n times log m plus n. So we want to reduce the time complexity of merging. That's why we need to leftist tree. So leftist tree is a binary tree optimized for priority queue operations. So the basic key operations like melding, inserting, and find maximum and minima, all the operations we will do using leftist tree in the minimum time complexity than the binary trees. Uh, the leftist tree are of two types. One is the height-based leftist tree, and the another one is weight-based leftist tree. I am going to explain about weight-based leftist tree. A binary tree is called weight balanced leftist tree if at every internal node the Wx of left child is greater than the Wx of the right child. So what is the Wx? Wx is a value. Wx store the value one more than the sum of the weights of its children. So now we calculate how we calculate the Wx for a node. Suppose that A, B, C, D, E. These are the nodes. So we want to calculate the Wx for the A. So A have four child. So the value of Wx of A is 4 plus 1, which is equal to 5. Now we want to calculate for B. The child of B is 1. The child of B is only D. So the value of B of Wx is 1 plus uh, 1 for D and plus 1. So the value of B is 2. So how we calculate the Wx of for each node, and there are some operations for WLT like insertion, deletion, and melding. So the main function is melding actually. We will do the melding top to bottom at each level when we will do a single operation at each level. That's why the time complexity of melding becomes log n, because the height of the binary tree or leftist tree becomes log n, and after that we will do the insertion, deletion, every mostly operations we will do in log n times. Now I am handling to my friend to explain about HBLT. Thanks.
Hello everyone, I'm Saurav Yadav, and let's continue further where my friend left. And now I will explain about the height biased leftist tree. Before going to the actual definition of HBLT, let's understand some terms related to the definition, which will help to understand the definition. Uh, Here we are calculating the S value for a particular node. For this, we will create um, create some external node by ourselves to make calculation easier. So these nodes are called extended node, and the binary tree which has such extended node is called extended binary tree. And we will take the s value of this node as a 0, and we will compare the s value of these two. Whichever value have minimum uh, will be taken by the this node, and we add plus 1 to this node, and again we will compare the x value of these two nodes, and 0 will be the minimum. It will propagate to this node, and we add for this node, we add 1 to for this node. So the s value of this node will be 1. Similarly, the s value of this node will be 1, and comparing these two we will get 0 is the minimum, and the s value of this node will be 1. And comparing the s value of these two nodes, we will propagate one to this node and add one to get the actual value of s value of this node, which is 2. And let's see how it will help to define the HBLT. So in HBLT, binary tree where the s value null path length of the left child is greater than or equal to the right child, means we will consider any node, and the next child of that node, left and right child, the s value of left child will be greater than the s value of the right child. And here it is the important property related to the hblt, that is s value is the length of the rightmost path from the node that is represented as x to the external node or extended node. Now, going ahead, here are few. This is the mathematical representation of calculating s value. That will be the s value equal to the minimum of s value of the left child and s value of the right child plus one. Means we will take the minimum of these two values and add one to the that value to get the s value of that particular node. Here it is the mathematical representation which will calculate the minimum nodes for a particular node with some s values, that is 2 raised to s value of that node minus 1. And here it will represent the um, maximum possible s value of a particular node with let's say m nodes, and that will be log m plus 1 base 2. Now going ahead, I'm going to explain about the initialization of hblt. This is a interesting method. For this, we will take n nodes. That is, for simplicity, let's take the number of nodes equal to some power of two. Like let's see, for example, we will consider 8. That is 2 to the power 3. So, to for next step, we will create n smaller uh, HBLTs of individual nodes, and we will store that smaller HBLT into a FIFO queue, and we will take two smaller HBLT at a time and uh, meld those smaller HBLT to create a bigger one, and put that newly built HBLT to the back of the queue, and we will follow this process until we will remain with the bigger HBLT, and at last we will have only one bigger HBLT. And the analysis of time complexity involved in this process is like this. Time to meld two smaller tree, means with each having nodes with equal to 2 to the power some I, means if the node is 2 and 2 for 2 smaller hblt, so the merging time will be big O of I plus 1. And we will calculate further for all the process to reach to the bigger hblt. We will read that the time complexity of initializing an hblt will be big O of n. Here are some important operations related to HBLT. Insertion, we will create single node HBLT and meld that with the existing HBLT. And when we are going to delete, HBLT will be either max or min. It's like a priority queue. Max if or min if, we can take as an analogy. Means we when we will create delete the max, we remove the root value max element and meld the left subtree and right subtree to get a new HBLT. And the important process which for which we are building the new data structure leftist tree is melding. So for melding, we will compare two hblts. We will have two hblts, so we compare the root of two hblts. The smaller root become the right child and maintain the access property by swapping if necessary. Means during the melding process, if somehow the s value of left child is smaller than the s value of right child, we will swap these two subtree to preserve the property of hblt. Here is the example of how the merging process work in HBLT. Like we will compare the root value of these two different HBLT. The one is the smaller, so we will take the uh, right subtree of this, and we will proceed. We will try to merge these two. We will compare the root value again. We will compare the root value of these two. The smaller value of root will be the 7. So we will take the right subtree of this, and we will again try to merge these two, and we again compare the s value of these two. So the 22 is smaller. Here we skip the one process. So here we will take the here the right subtree is like null. So we merge the null with 25, and we will backtrack to get this, and from the here we will build SBLT by these three nodes, and we will take this to merge with the this one, this smaller SBL part of SBLT, main SBLT, and we will merge these two, and here the merging part, and we don't need to swap this because the value of this node and the value of this uh, right subtree, right child of the 7 is equal, so we don't need to swap. Again we will merge this subtree to this one, and we will find that the s value of this is 2 and s value of this is 1, so we need to swap this. So we swap the right subtree and left subtree to get the merged HBLT. During this process it will take log n time, so it is efficient to merge using HBLT. Now here is the small comparison between HBLTs and the WBLT, which is discussed by my friend, like balancing property, height Sx and weight WX means in HBLT we use Sx value which is depend on height, and in WBLT we will take the W value which is based on weight, and melding complexity is log n, big of log n is same, but WBLT is somewhat faster than H- HBLT. In arbitrary dilation means it supports in HBLT if we have pointer, and it will take big of log n to delete, but in WBLT it is not efficient. And application like HBLT is generally used in priority queue, and WBLT is specialized use cases. Now, over to my friend Deepak to discuss further.
Hey, my name is Deepak. As Saurabh shared, I'm continuing with the slides. So let's talk about the application of leftist tree. The very first uses came into the priority queues, which is like it mm, like priority queues is well suited in the efficient heap merge, which is a common operation in all priority queues. And by using the leftist tree, it also ensures the quick insertions and deletion, and access to the highest priority element in the priority queues, which is also facilitated by leftist tree. And second use cases comes in the graph algorithms, which particularly speaking in Crucial's algorithm for finding the minimum spanning tree, and it also efficiently handle merging of edge sets during the algorithm executions in the graph algorithm. Third uses came into the dynamic set operations, which facilitate the fast merging of disjoint sets, which is a which is a like frequent requirement in the dynamic set problems. So these are the some of the application which uses like which efficiently help these data structure to facilitate their operations. Now come to the implementations of the like a very short and full implementation of the leftist tree, in which we define the first class, which is a node class. It is the node that will form our leftist tree. So it has four parameter. Key is the value of the node. Left and right are the reference of the left and right nodes, or we can say that subtrees. And s is the null path value which we are like going to calculate in that. And these implementation are based on the height biased leftist tree. So this is the node signature class. And we define the meld function. Meld is nothing but a merge operation which take two unlike parameters, like two argument, which is h1 and h2. H1 and h2 are the two trees which we have to merge. And in the very first lines of the function, we are checking if one of them found to be a null, like a tree which is a null, then we are just returning the second one as a merge tree, because we doesn't make any sense of merging a one tree with the none. So in the oh it's in, so in the next line we are checking or like finding on the which leftist tree root is greatest. Like as Saurabh and Saurabh discussed that in the merge operation we have to um, merge with the highest root node tree with the lowest root node tree. So we are, if we found to that s2 is the greatest in the root node value, then we are exchanging, like swapping them. And after that we are recursively calling h1 h1, like, or we can say that the which root node's value is highest subtree with the s2. So after recursively calling the meld operation on h1 dot write with the s2, we are checking there if we, like, again it's checking if we found to be any of them none, or we are getting the h1 right dot s value greater than h1 left value. It is just a leftist tree order that we have to maintain in the height bias leftist tree, which is just a subtree sub left subtree value must be greater than or equal to the right subtree's value. Or if it found to be wrong, like if it found to be false statement, then we just swapping the right subtree with the left subtree. And in the last uh, we are just assigning the value or s value, which is a null path value, shortest null path value, to the h1 which is nothing but a root node of the merge, like the resultant tree, and returning the h1 which is just a resultant tree that we merged. And now there are two more function, which is nothing but a delete and insert operation. In the insert operation we just have to create a node with which element we have to insert, like I'll create a new node and call the merge, or we can say that meld operation with that, and it automatically merged with, like, meld with the tree. And in second delete max, in that we don't have to do anything, we just have to call the meld operation with the left subtree and with the right subtree, and it get merged, and maximum element, which is nothing but a root node, get deleted. So these are the example. Now let's come to the summary, as we gone through the types of the leftist tree and what are the leftist tree, how it works. So these are, like, you also get to know these are efficient tree based structure for priority queues, dynamic sets, and graph algorithm. Generally it uses in priority queue, which is generally uses the heap property. In heap we use merge operation, which is facilitated by these leftist trees. And the second was key, what is the key difference between the height bias leftist, oh, it's balancing criteria. It by, like, height, in height bias, as we seen that we are like focusing on height or the null shortest null path value. And in the weight we are just concerned about the number of nodes in the both subtrees. So these are the differentiating factors that we are, like, concerning about in both variant of the left and whatever. So in, like, all, and the application also has been also discussed, like it used in graph algorithm and dynamic sets theory. So these are the very simplest explanation of leftist tree. And just we are done with the, so here are the references. So we use the data structure and application like handbook, or which is found written by S2 and S Sahani, and we taken help from Geeks for Geeks org and W3 School. Some of the references were taken from there. And lastly, thank you everyone for giving your invaluable time for listening this. I hope it helped you in some way.